Hello everyone. So now we will start with the next topic, that is FIR and IR filter implementation in fixed point systems. So in that, first we will start with the FIR filters that is implemented in fixed point systems. So later we will start with the IR filter, because till now you not studied about IR filters, which will be the module 4. So I will cover this topic, IR filter implementation, once we will completed this model 4. So now we only concentrate on FIR filter implementation in fixed point systems. So here in this topic we are going to discuss how the digital filters like FIR filter will be implemented using a system or the number system like fixed point system. Okay, so here, as we know that the fixed point system uses the queue format, and we already studied in the fixed point system that so to perform any multiplication or addition, so we are using a standard Q15 format, so which controls the overflow of the result. So using that concept in fixed point system, we are going to implement a digital filter like FIR filters. Okay, so now I'll move on to the topic. So this is finite impulse response filter implementation in fixed point systems. So as we already know that here the digital filters like FIR can be implemented using direct form 1, or you can use it in a cascade forms. There are some other techniques like parallel, direct form 2 also. So that we will discuss in the IR filters. These are the other ways where we can implement the digital filters like FIR filter. So our intention is we need to design a filter which has a passband gain and the stop band gain. So filter means it should filter the unwanted frequency components and only allows the frequency components which needed for the output. So here this is a kind of a filter which performs the same thing like a normal filter, but only thing is that we are implementing it in fixed point system. So when we are implementing it in a fixed point system, so it should follow the queue format of the fixed point system. As we know that the queue format of the system is like this. So this is the queue format number representation, the most common one, which is used for the fixed point in the DSP implementation. So this Q15 format has the first bit is sign bit, remaining 15 bits are magnitude. So whatever the input data or the coefficients or the output data, so once you perform any operation on the input data using coefficients of the input, the coefficient and the output should be within the range of this Q15 format. Then only it can prevent the overflow of the design. I hope you guys getting this what I am saying. If you filter any input data at the output side, so the input data is provided with the coefficients like the impulse response. That coefficient and the magnitude of the input data should be within the range of this Q15. So in that Q15, this is always measured in terms of fraction part. Okay, because here I have taken as 2 raised to 0, 2 raised to minus 1, minus 2, minus 3. This indicates that the value of this Q15 format is always less than 1. So any data, either the input or the coefficient, which is given for this digital filter should be less than 1. Otherwise, it should be scaled down. So that is what we are going to discuss here. So here in the fixed, this is written here in the fixed point system where only integer arithmetic is used, because we are going to perform only the arithmetic based on integer numbers. So we prefer input data, filter coefficients, and the processed output data should be in the Q format. So if these are not in the Q format, that is Q15 format, then there is an overflow when we perform multiplication and addition. So because of this, whenever the input data and its coefficients are given to the filter, first thing is that you have to observe either the input and the coefficients are less than 1. If they are not, first you have to scale them down. And the formula which is used to scale them down is this one. We call it as equation 1. S equals to I max summation of k equals to 0 to infinity magnitude of h of k. So this is a standard formula which is used just to find out the scaling factor once the input data and the coefficients are greater than 1. So whatever may be the passband gain, I am not talking about the passband gain because for every filter there is a passband and there is a stop band. So for this implementation using fixed point method, passband gain has no limits. It will be a greater than 1, okay, but the input data and the coefficients of the input should be less than 1. Where in this formula, if I expand this from k equals 0 to infinity, so we will get it as I max into h of 0, h of 1, h of goes on up to infinite. So here h of k is nothing but impulse response of the adder. This is an adder, okay, that's the impulse response of the adder, and I max is the maximum amplitude of the input in Q format. So but still this is not an optimal factor in terms of reducing signal to noise ratio, that is S by N ratio, because here the output which we are going to obtain should be or must be in a clear information. Whatever the input you have sent, you should get at the output side. But still there is some noise present at the output, even though we are filtered. So, but still we can prevent the overflow using this equation 1. But the output is not much clear, but we can still prevent the overflow. And the output of this adder is always in terms of convolution output, because this impulse response of the adder will multiplied with the input signal x of n. So that's why we get the adder output as h of 0 into x of n, h of 1 into x of n minus 1. So like this, the output will be in the convolution output. Even though we have taken the scaling factor with respect to the impulse response and its magnitude, this magnitude is nothing but the input data magnitude. Therefore, it involves with the input signal in terms of convolution output. So to understand this, how the scaling factor is done for the input data and the coefficients. So let us take one example here. Okay, the same thing is explained. So let us take one example here. So as shown in the figure 1, it describes the implementation of the digital filter like FIR. So using direct form on method. So in this direct form on method, here the factor b makes the coefficients like bk divided by b. That is nothing but b is a scaling factor which is used to scale down the coefficients, whereas s is the scaling factor which is used to scale down the input. But the condition is that s and b should be chosen with the power of 2. If I got any value, that value should be nearly equals to the power of 2. So we'll understand this. To scale down, you have to do the division, and that can be accomplished using shift operation. If I shift to the left or to the right, can perform multiplication and division. So using shifting operation, we can implement the scaling factor operation using codes also. Okay, so now let us take one example here. So this is a direct form on implementation of FIR filter. So what it consists of? We have a x of n, that is input signal. So before the x of n given to the this implementation, that is the digital filter, first the input signal x of n should be scaled down by a factor of s. So this is the device which performs that operation. So this device scale downs the x of n by 1 by s and gives us the another scale down input like s of n. Similarly, we have to scale down the coefficients of this xs of n or the input signal. For that, we will use a b factor. What this b factor does? This b factor scale downs all the coefficients before it reaches to the output. So here, this is a first coefficient like b naught, scaled down by b. Next, once xs of n minus 1 goes through the delay, we will get another coefficient, it is b1, scaled down by b. Like this, till goes on up to the bk coefficients. Depends on the input. So once they are scaled down, here we have scaled down both the input and its coefficients using s and b factor, and we got the output ys of n. Ys of n is the output which are obtained after the scale down of input data and its coefficient. But we need the actual output data. So to get the actual output data, again we should scale up this ys of n, okay, by using the same scaling factor like b and s. After that, we can obtain the original information. The scaling factors are used just to prevent the overflow and keeping the input coefficient and output within the Q format. So let us take one example here. So in this example, they have given one FIR filter, so which is y of n equals to 0.9 into x of n plus 3 into x of n minus 1 minus 0.9 into x of n minus 2. So in this, first you have to observe the coefficients. So the coefficient here, the second coefficient, is greater than 1, means now we have to scale down the coefficients. With respect to that, we have to scale down the input signal also. Suppose if the x of n, for example, if n is 0, so we will get x of 0. That x of 0 value may be greater than 1. That is the amplitude like Imax. So if it is greater than 1, then it should be scaled down by less than 1. So first they have given the output response in terms of x of n and its coefficients. So they have given the passband gain is 4 here. Assuming that the input range occupies only 1/4 of the full range, means the maximum magnitude of the given input signal is 1 by 4. So now we have to develop the DSP implementation equation in a Q15 fixed point system, means you have to develop the equation which should be within the range of Q15 fixed point system. So how to solve this one? First thing, you guys need to find out the scaling factor for the input and the scaling factor for the coefficients, and you should remember these two should be the power of 2. Okay, so first thing, the adder may cause, this is a solution I am going to start. This adder may cause the overflow if the input data exists for 1 by 4 of a full dynamic range. The scale factor is determined using the impulse response, which consists of the FIR filter coefficients. So here the Imax value is given as 1 by 4. So you know the scaling factor formula, which is given like this here. So this is the scaling factor formula. I am going to substitute in this to get the scaling factor. So Imax is 1 by 4. So only the n value ranges from here 0, 1 and 2. So n ranges from 0 to 2. So written h of 0, h of 1 and h of 2. H of 0, 1 and 2 are the coefficients. We have taken as 0.9, 3 and 0.9. So here only consider the positive values of the coefficient. Negative is associated with the input. That's why we have considered only the 0.9 values which is positive. So then it should be divided by 4. We got it as 1.2. But the condition for the fixed point system is that it should be with the power of 2. So the nearest value for the 1.2 with the power of 2 is 2 raised to 1. So we can write it as 2 now. So S can be chosen as 2, and the factor B should be the next power of 2. So if I choose 2 raised to 1, the next power of this B factor is 2 square, that is 4. So therefore we have chosen S equals to 2 and B as 4 here. So now using these two scale down factors, we can scale down the input data and the coefficient, which is shown here. So here this is the scale down input signal x s of n, which is given by xn of by 2, because x of n is the complete input signal which is given for the filter. So in that it should be scaled down by 2. So we have written xn by 2 is nothing but x s of n, which is the scale down input. Similarly, we have to scale down the coefficients. How to do that? So to obtain y s of n, we have to scale down this input by 4 now. Only the coefficients, like 0.9 should be divided by 4, 3 is divided by 4, again 0.9 is divided by 4. So if I divide them by 4, we got it as 0.225, 0.75 and 0.225. And you observe that all coefficients are less than 1 now. So x s of n gives the scale down input by 2, and y s of n gives us the scale down coefficients. So once we got the scale down input and the coefficients, they should pass through the filter and we get the obtain the output y of n. So before getting the y of n should be again scaled up. So that should be scaled up by this value, that is the factor b and the factor s here. Factor b is 4, factor s is 2. So 2 into 4 becomes 8 now. So this y of n now should be multiplied by 8 to obtain the original output y of n. So which is shown here, that is y of n is the output which is obtained by 8 into ys of n. So like this, the FIR implementation is implemented using fixed point system. I hope it is clear for everyone. So just give another question. So just you try it on your own. So in the given question, they have given y of n equals to this much, with the passband gain is 4 and the Imax, that is 1 by 4. So repeat this above example only for these values now. So try on your own to obtain the output. Okay. So once you got this, and submit the assignment when I send you the link. So here check y of n equals to, here instead of 0.9 choose 0.6. Okay, this is take it as 0.6, and instead of 3 take it as 0.4. Okay, and here instead of 0.9 take it as 4. Okay, make this as positive. Repeat the above example, only change the coefficient and change the value of 1 by 4 to 1 by 2. So these are the altered values which I have given right now. So try this on your own, okay, and prepare the answer. So in the next class, I'll ask you guys about the answer and the scale down factor which you have chosen. Remember, to select the scale down factor, it should be the power of 2. If you got it as 0.8 as a scaling factor for s, then this should be nearly equals to 2 raised to 0, that is 1 here. If you got greater than 1 point something, then 2 raised to 1. If you got 2 point something, then 2 raised to 2. So like this, you have to select the scaling factor. Based on that, you have to select the b factor also, which is greater than s factor. So I hope it is clear for everyone about FIR filter implementation using fixed point system. The same thing will be done for FIR filter, that we will discuss once we start a discussion in the module 4. Okay, so thank you. We will wind up the class now.